Welcome to today's episode. We're diving into the fascinating world of generative models with an expert who's been at the forefront of some groundbreaking research. Can you introduce us to the concept of consistency models and why they're important?
Absolutely, it's great to be here. Consistency models, or CMs, are a new class of diffusion-based generative models. They're designed to tackle one of the major hurdles in traditional diffusion models: slow sampling speeds. Imagine trying to create a high-quality image, but each step takes a considerable amount of time. CMs optimize the process, making it much faster, which is crucial for applications like real-time image synthesis.
That sounds like a game changer. What about continuous time formulations? How do they fit into this picture?
Great question. Continuous time formulations are like a smoother version of the process. They reduce discretization errors, which are essentially small inaccuracies that accumulate when you break a process into steps. However, they come with their own set of challenges, particularly training instability. It's like trying to balance on a tightrope. The potential is huge, but you need to be very precise.
So how do you address these challenges? Is there a solution?
Yes, and that's where the TrigFlow framework comes in. TrigFlow unifies two powerful concepts: EDM and flow matching. By bringing these together, it simplifies the formulation of diffusion models and stabilizes the training process. Think of it as creating a sturdy bridge that allows us to cross the tightrope with ease.
Fascinating. Can you tell us more about the improvements in training these models?
Certainly. We've introduced several enhancements. For instance, better time conditioning and adaptive group normalization help the model understand and adapt to the data more effectively. We also reformulated the training objectives, especially for continuous time CMs, to make the process more stable and efficient. It's like giving the model a better map and compass to navigate the complex landscape of data.
And what about scaling? How do these models perform when they get larger?
Scaling is where things get really exciting. We've managed to push these models to an unprecedented scale with 1.5 billion parameters. This allows them to achieve performance levels that were previously out of reach, narrowing the gap with state-of-the-art models in terms of FID scores, which are a measure of image quality. It's like upgrading from a bicycle to a high-speed train.
What are the main challenges you faced along the way?
Training instability was a big one, especially with continuous time models. There's also the high computational cost and complexity of existing diffusion distillation techniques. These are like the bumps and hurdles on the path to innovation.
How did you overcome these obstacles?
We tackled them by introducing TrigFlow, which simplifies the framework, and employing adaptive techniques like tangent normalization and warmup. These methods help stabilize the training dynamics, making the process smoother and more reliable. It's akin to having shock absorbers on a rocky road.
What broader implications do these advancements have?
The implications are vast. Faster and more stable generative models can revolutionize fields like high-resolution image synthesis, enabling new applications in industries ranging from entertainment to healthcare. Imagine creating detailed virtual worlds or enhancing medical imaging with unprecedented speed and accuracy.
That's incredible. As we wrap up, what future directions do you see for this research?
The future is bright. We're looking at refining these techniques further, making them even more efficient and accessible. There's also potential for exploring new applications beyond image synthesis, such as video generation or even complex data simulations. The horizon is wide open, and we're just getting started.
Thank you for sharing these insights. It's been a pleasure having you on the show.
Thank you for having me. It's been a joy to discuss these exciting developments.